Hello everyone, can you see my screen? So we will wait for a few minutes and then we will start. Let others join. Hello everyone, a very good evening to all. I welcome you all again to the interaction session on Experimental Physics 1, which is being flowed this semester by NPTEL. Myself, Vivekananda Naik. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So let's discuss a few problems and other experiments that you have covered in the past week of the lectures. So uh, during the past week, we discussed about the experiment uh, determination of coefficient of viscosity of a liquid. So we will continue our discussion. We will solve a few problems related to the viscosity of liquid. Now the first problem is the viscosity of a fluid is 2 poise. What is its value in Newton into second per meter square? So can anyone tell me what is the dimensional formula for coefficient of viscosity? Yes, anyone? Can anyone tell me what is the expression for coefficient of viscosity?
Hello, sir.
Yes.
So the dimension of viscosity is m l minus 1 t minus 1.
Yes. So what is the formula for viscosity? The coefficient of viscosity. Suppose if the coefficient of viscosity is eta, then eta is the ratio of trace and velocity gradient dp by dx, because we have discussed that since the liquid flows by layer, or a liquid consists of a number of layers, so the layer, suppose this is the wall, this is the pipe wall, so the liquid which is close to the pipe will be moving in a lesser speed, and then gradually at the center of the water flow, the velocity is maximum. So there is a velocity gradient as we go away from the center. So it is r equal to 0, and it is r equal to radius of the tube. Then there is a velocity gradient. This is this velocity gradient. And since there is a viscous force or viscous drag, because since liquid is flowing through, you see, liquid is flowing in terms of a number of layers. So when one layer goes over another, there is a viscous force or viscous drag which is in opposite direction, because since liquid is flowing in this direction, so there will be pressure, more pressure will be on this side and less pressure will be on this side. There will only be, so this is the force due to pressure, and in the opposite direction this is the force due to viscosity. So this is the expression for coefficient of viscosity. So basically what is the, so since this is the formula for coefficient of viscosity, we can say that the unit is, we know that the unit of viscosity is, in the coefficient of viscosity, eta is poise or decapoise, poise or decapoise. So 1 poise is equal to, but how much? 1 poise is equal to, if you take here, F will be in
0.1.
no, I am saying what 1 poise is equal to what? If you compare this expression, since the unit of eta is poise, then 1 poise will be what? If you compare this expression, it will be 1 dyne divided by 1 centimeter square whole divided by, this is dv by dx. So dv by dx is dx by dt by dx. So this cancelled out. So it will be only dt in the numerator. So it will be 1 dyne into 1 second divided by 1 centimeter square. So this is the expression for 1 poise. So 1 poise is 1 dyne into 1 second divided by 1 centimeter square. Also, we can say that if we compare this expression, we can also say that if a force of 1 dyne is required over an cross-section area of 1 centimeter square to maintain a velocity gradient of of 1, this is velocity dx by dt divided by dx. So it will be 1 second inverse. So a unit velocity gradient. So 1 poise is equal to the amount of force required to maintain a force of 1 dyne for 1 centimeter square of cross-sectional area to create a unit velocity gradient. So this is the expression for 1 poise. It is 1 dyne into 1 second by 1 centimeter square, but we have to convert it into Newton into second per meter square. So 1 dyne is how many newtons? Anyone? No? 1 Newton is 10 to the power 5 dyne. So one dyne is 10 to the power minus 5 Newton, 10 to the power minus 5 Newton into second is there, and then 1 centimeter square will be 10 to the power minus 4 meter square, because 1 centimeter is 10 to the power minus 2 meter. So 1 centimeter square is 10 to the power minus 4 meter square. So if you convert, or if you calculate all this, it will be 10 to the power minus 1 Newton into second per meter square. So it will be 0.1 Newton into second per meter square. So this is the correct answer. So the correct here it will be 0.1. This option will be not 1, it will be 0.1. So this is the correct answer. So since it is 0.1, but here the question, sorry. But in question we need to find out the here it is given the viscosity of a fluid is 2 poise. So since it is 2 poise, so 1 poise is equal to 0.1 Newton into second per meter square. So 2 poise will be equal to 0.2. This will be the correct answer because it is 1 poise. Then 2 poise will be 0.2 Newton into second per meter square. And the dimensional formula for this coefficient of viscosity is M1 L minus 1 T minus 1. Is this clear to all of you? Yes. Is this clear to all of you? Basically, in the question it was given that what will be the value of 2 poise in terms of Newton into second per meter square. So we know according to the definition of coefficient of viscosity, it is stress per velocity gradient. So if you take 1 poise unit, then it will be 1 dyne divided by 1 centimeter square, and then there will be 1 dV by dx. So dV by dx is nothing but the dimension of dV by dx is time inverse. dV by dx is time, so it goes above and it is time inverse. So the dimension formula is M1 L minus 1 T minus 1. So 1 poise is equal to 1 dyne into 1 second divided by 1 centimeter square. And we know 1 dyne is 10 to the power minus 5 Newton and 1 centimeter square is 10 to the power minus 4 meter square. So if you convert, 1 poise will be 0.1 into 0.1 Newton into second per meter square. So 2 poise will be 0.2 Newton into meter per second square. So the correct option will be C. And also the unit decapoise. This decapoise is 1 decapoise is 10 poise. Commonly used units of coefficient of viscosity. So now let's go to the next question. Question says at the bottom of a uniform cylindrical vessel of 30 centimeter height, a horizontal capillary tube of 2 mm inner diameter and 10 centimeter length is connected to discharge the liquid. Calculate the rate of discharge of the liquid if the vessel contains water of viscosity 0.01 poise to its 2/3 capacity and the given value of density of water is 1 gram per centimeter cube. So this is the question and the options are 6.59 centimeter cube per second, 7.69, 8.25 or 9.24 centimeter per second. So basically we need to find out the rate of discharge, that which is in volume per second. Now we had discussed in the previous class how for performing the experiment there is a working formula. So the question is simply Based on that working formula, you need to put the formula and calculate the value of the unknown, which is the rate of discharge of the liquid. So I will be giving you a few minutes. Please try to solve it and tell me what will be the correct answer. After that, I will discuss. Yes, anyone solved it? Can anyone tell me what will be the rate of discharge of the liquid? Sorry, can you say it again? Your voice is breaking actually. So I can't hear you properly. So let's solve it. So if you remember in last class, we had derived that the formula for the rate of discharge of the liquid dV by dt is equals to pi delta P divided by 8 eta L into R to the power 4. So this is the formula where R is the radius of the capillary tube, then L is the length of the tube, and the and in question it is given cylinder of 30 centimeter height in a horizontal capillary tube. At the bottom of a uniform cylindrical vessel of 30 centimeter height, the calculate the rate of discharge of the liquid if the vessel contains water of the viscosity eta is given 0.01 and the capacity is 2/3 of the whole total capacity. So now this delta P, we know the pressure due to a liquid of certain height is H rho G. This is the pressure head or pressure associated with a liquid of height H. So if you use the formula, suppose this V is the dV by dt or rate of change, rate of discharge of the liquid, then the value will be pi into H rho G into R to the power 4 divided by 8 eta L. So pi is 3.142 into H. So H is 2/3 of the vessel contains water with 2/3 capacity of 2/3 capacity. So the vessel height is 30 centimeter. Its 2/3 capacity means it is 2/3 of 30 centimeter. 2/3 of total height of the cylindrical vessel. Then G, since we are calculating in centimeter cube per second, so we will be putting G 980 centimeter per second square, and then R is, it is 2 mm. 2 mm means 2 mm inner diameter. So it will be 2 into 10 to the power minus 3 meters. So it will be 1 into 10 to the power minus 3 meter. So this will be 1 into 10 to the power minus 3. I think this 1 minute, let me check. So this is 1 10 to the power minus 3 into eta is 0.01 into, sorry, since we are doing it in centimeters, so this 2 mm is, if you convert it to centimeter, it will be 0.2 centimeter. So the radius will be 0.1 centimeter. So there will be is 0.1 centimeter to the power. This is 0.1 to the power 4. Then 8 into 0.01 into length is 10 centimeters. So this is 10. So if you calculate all these, it will be coming around 7.69 centimeter cube per second. So can anyone tell me what is the alternative unit of centimeter cube? Yes, can anyone tell me? Centimeter cube is otherwise called as centimeter cube is otherwise called as ml. So 7.69 centimeter cube per second means 7.69 ml per second. So this is the rate of discharge of the water. So the correct answer is 7.69 centimeter cube per second. So now the next question. The question says, what do we call the maximum velocity of a fluid in a tube for which the flow remains streamlined? So it is basically it is a conceptual question. Question says, what do we call the maximum velocity of a fluid in a tube for which the flow remains streamlined? The answer will be critical velocity, because this is the maximum velocity of the water when the water is streamlined. So this is the critical velocity, VC. This is the maximum velocity of fluid in a tube for which the flow remains streamlined. Also, if you there are different for a particular fluid, there are different types of flows. Like there are molecular flow, laminar flows, then turbulent flow, then streamlined flow, like that. So all these flows are basically determined in terms of a number which is called as Reynolds number R. So if the Reynolds number is less than 100, then it is the flow is streamlined. If the Reynolds number is greater than 2000, the flow is turbulent. So if it is 1000 to 2000, then the flow is unstable, or it is changing from streamlined to turbulent. So for streamlined flow, like if the flow is streamlined, then we can say that fluids are flowing in layer by layer. So this is streamlined flow, and the maximum velocity of a fluid, if the fluid is flowing in a streamlined mode, is critical velocity. Taking the next question, which of these ratios give the value of coefficient of viscosity of liquid? Can anyone tell me what will be the correct answer? Because we know coefficient of viscosity is what? F by A divided by dV by dt. Is not it? So can anyone tell me what will be the correct answer? Yes, can anyone tell me which of the ratios?
D, sir.
Yes, the correct answer is the ratio of shearing stress to the velocity gradient. Because if you see all the options, the first option is shearing stress to weight of the liquid, weight of the fluid. This is not correct. This is velocity gradient dp by dx. So we know the velocity gradient will be in the denominator. So correct answer will be D. So the ratio of shearing stress to the velocity gradient. Is this clear to all of you? So now let's discuss about oscillation, because the next experiments are related to the type of oscillations like force oscillation, free oscillation, damped oscillation, etc. So let's discuss a few things about oscillation. Now, when do we call object is oscillating, or something is oscillating? So if it repeating its values, so oscillation is defined as the process of repeating variations of any quantity or measure about its equilibrium value in time. So basically, if a quantity is oscillating, suppose this is a quantity, this is its average value, and the quantity is oscillating like this. So with time, the quantity is oscillating, and it will be the equilibrium value of quantity is this straight line, and the quantity with time is oscillating like this. So we can say it as oscillation. Basically means periodic change or repeating variations. So there are different types of oscillations. Also, oscillations can be defined as a periodic variation of a matter between two values or about its center value. Like if it is two value, one value is here, one value is here. This is its maximum value. This is minimum value. So it is suppose this is maximum, this is minimum. It is oscillating like that. So this can also be called as oscillation or about its central value. Or if this is a central value and it is oscillating around the central value. So this is the central value. Here this is the maximum value, and this is the minimum value. So basically oscillation means variation or change in its value corresponding to a particular level. If it may be changing between two values. One is maximum, one is minimum, or it may be changing around a particular value, which is called as average value. So there are different types of oscillations, like free oscillation, forced oscillation, and damped oscillation. So when we can say that the oscillation is free oscillation? So when a body vibrates with its own frequency, this is called a free oscillation. The free oscillation has a constant amplitude and the period without any external force set to oscillation. So if a body is oscillating in such a way that during the time of oscillation, its amplitude remains constant and its time period or frequency of the amplitude is also constant without any external force. Here we know free means there are no force applied. So without any external force, if the amplitude of the oscillation remains constant and the time period or frequency of the oscillation is also constant, then we can say that this is free oscillation. For example, we can take the vibration of a tuning fork can be assumed to have a free oscillation, but generally due to different types of forces which we can't avoid, almost all the oscillations in nature are not free oscillations. They are generally damped oscillations because they have some external force. They have some external force due to which the amplitude goes on reducing as the time increases, the amplitude goes on decreasing or reducing. So then what is damped oscillation? Most free oscillations eventually die out due to the ever-present damping forces in our surroundings. So if you see, suppose you take example of a simple pendulum. So when it will be, suppose this is a simple pendulum. So the equilibrium position of simple pendulum is here. So it has minimum energy here. So if you take it here, suppose this is 0, then it is some height h. Suppose this is the height h, then some energy is stored. So when you leave it here, so due to the weight, because this has some weight mg, this weight mg, and here the tension T is balanced, so it is at this equilibrium position. But when you take it here and then leave it, then due to the weight mg, it will be they will be having two components, so it will be coming back to its original position, and then it will overshoot the original position and it will start oscillating. But suppose this is the distance, and suppose this is the base distance and this is the height it gained. So this is the amplitude of oscillation. But if you see, as the time increases, the amplitude or the oscillation dies out because there is friction of air. So the oscillation that decreases with time is called damped oscillation due to the external factors such as friction or air resistance. So due to air resistance, the oscillation amplitude is decreasing gradually. So this is an example of damped oscillation. Also, due to this damped oscillation, the energy is also being lost from the system, and eventually it will come to rest. That is its minimum energy position or most stable position. And then there comes forced oscillation. Forced oscillation means, since we saw that in case of damped oscillation, the amplitude is changing or amplitude decreases gradually. But in case of forced oscillation, there is another agent or another force. Like in damping oscillation, the force is called a damping force. This is the damping force. But in case of forced oscillation, when something oscillates by being influenced by an external periodic force. So if you apply some periodic force to that oscillation, then for that particular oscillation, the amplitude will be increasing or decreasing. It will depend upon the external periodic force. So this is called as forced oscillation. Also, we can say that damped oscillation may be a special case of forced oscillation. Here, the amplitude of oscillation experiences damping but remains constant due to other external energy supplied to it. Suppose, similarly, we can take the same example. Suppose we are oscillating the simple pendulum, but when suppose this is the in fast oscillation, this is the height it went above its equilibrium position. But as time goes on, as time increases, the height will be decreasing and it will eventually come to its equilibrium position. But if we apply when the pendulum is here, if we applied some force so that without any decrease in its amplitude, the pendulum comes here, then again when due to the damping nature or friction of air, again the amplitude decreases. We will be again applying some force. So there is a periodic force which helps in maintaining the constant amplitude. So this periodic force, this is the called as periodic force, and this periodic force has also a frequency of its application, because only when there are two frequencies, like one is the frequency of oscillation and another is the frequency of periodic force. So when these two forces are equal, then the amplitude will be increasing with time. So this is called, the condition is also called as resonance. We'll be discussing about it in a few minutes. So for you can take simple example again. Another example maybe when you play with a toy that involves an object being supported by elastic suspense, like this is a elastic suspense. In the beginning, if you hold your finger still, the object bounces up and down with a small amount of damping. But if you move your finger up and down, the object will follow along. So this is another example of forced oscillation. So this the if you move your finger up and down, so this movement of finger up and down, this is the periodic force which we are applying, and this the object bouncing up and down is the oscillation. So if the frequency of this object up and down or bouncing of the object becomes equal to the frequency of the finger, that is the frequency of the periodic force, then your object will follow along. So now in terms of mathematical expressions, we can say that in case of free oscillation, now generally per oscillation its amplitude changes with amplitude remains constant. So but according to the time its value changes. So we can take it x t equals to a sin omega t, then velocity by taking first derivative with respect to t, it will be minus a omega cos omega t, and then again taking derivative. So vt is nothing but dx by dt, and at is d square x by dt square. So it is minus a omega square sin omega t, or simply we can say that minus omega square x. Is not it, because x is nothing but a sin omega t. Basically, generally we can take x equal to e to the power I omega t, then it will be cos omega t plus I sin omega t. So here we have taken only one component, that is imaginary component. Also we can take only real component or cos omega t, the value will be same. Basically, why, can anyone tell me why we generally take the exponential function when you consider any type of displacement in case of oscillation? This e to the power I omega t. Yes, can anyone tell me? If you see, if you take x equal to e to the power I omega t, again this acceleration at will be again minus omega square x. You can try. If you take derivative again, dx by dt, it will be minus, it will be I omega e to the power I omega t. Then if you take second derivative, it will be I omega into I omega, it will be minus omega square e to the power I omega t. So it will be again minus omega square x. So here we have taken only sine component or imaginary part, but generally during all the calculations or derivations, we take exponential function, because exponential function is one of the simplest function in terms of its derivative and integration, because we know the integration of an exponential function is again exponential, and similarly the derivative of an exponential function is exponential. So exponential function is generally taken due to its simple calculus, due to the involvement of simple calculations related to the use of exponential function. So if you apply the Newton's second law of motion here, then we know there is a restoring force always. So this restoring force is called as minus kx, like in spring constant, due to the force, due to its weight mg, it was experiencing some force. Due to its weight, it was experiencing force mg, and due to that force, since it is in equilibrium, this force is balanced by this restoring force. So this force, according to Newton's second law, this is mass into acceleration. So this is the equation of motion, and if you apply here, a is minus omega square x. So if you apply, so it is omega 0 square. If you compare these two values, so omega 0 square is k by m, or omega is k by m root. So this is the frequency of oscillation, or angular frequency of oscillation, and this is the equation of motion. This and the solution of this equation is x equal to a sin omega t, or a cos omega t, or a e to the power I omega t. So, and also you can say, since the oscillation is free, the amplitude remains constant, and also the time period is constant, because the time period here is equal to the time period between these two intervals. So now talking about damped oscillation, the equation of motion changes because there is a damping factor. So as you can see, the equation in the equation of motion, this is the acceleration term, and this is the oscillation or restoring force term. And since there is a damping force, another damping force, and basically damping forces are non-conservative because they do some work, and since and according and due to that properties, we can say that they are velocity dependent. So they have expression. So this is the damping component, this is the restoring force, and this is the acceleration term. So damping gamma is P by M, which is called as the damping constant, and this P by M has the dimension of frequency. If you compare, because all the terms have similar dimension, since d square x by dt square has the dimension of acceleration. So if you compare it, dx by dt has the dimension of velocity. So it will be dx by dt square. So this will be 1 by t. So the dimension of gamma is frequency, that is 1 by t, and this p is called as coefficient of damping force. So if you solve this equation, its general solution will be xt x0 cos omega t plus phi. If you take at initial condition, this is the phase. If the phase is 0, then simply we can say that it will be x0 e to the power minus gamma t by 2 cos omega t only. And you can see that there is an exponential factor here. So the position goes on decreasing. So this is x and this is t. So you can clearly see the graph is this is the graph of this is the sine graph. So we can say that this curve, this envelope is e to the power minus gamma t by 2, and this black one is of sine or cos. Any, like in plotting of graph, you can say that if there are two functions and and the product is plotted, then the profile will be like that, because this x0 e to the power minus gamma t by 2 is the amplitude. So this is the amplitude. The envelope will be exponentially decaying, because the exponential decaying graph is like that. This is the graph of e to the power minus x, and since there is another term here cos omega t or sin omega t, then the profile will be like that. Then if you see, depending upon this damping constant, if the damping is if the value of the constant is low, then it is called as underdamped. Then if the constant is corresponding to a particular value or equal to a particular value, then it is called as critical damp. And then if the value is very greater than, then it is called as overdamp. And this is the basically the different profile of the. So as you can see that this is over damping, 1 is green is over damping, 2 is critical damping, and 3 is under damping. So this is the profile of damped oscillation. Now talking about forced oscillation, the in case of forced oscillation, since as we have discussed, in case of forced oscillation there is a periodic force and it has some frequency. So if you see in the equation of motion, this is the equation of motion of a forced oscillation. This term is present, it is due to the acceleration of the system. Then this is the restoring force, then this is the damping force, and this is the applied force, and it has some frequency omega. This f0 sin omega t is the frequency of the force that is being applied. And if this force, if this frequency of this force is, so if you solve this equation, it will be xt a cos omega t plus phi, but here a is f0 divided by m square omega square minus omega 0 square whole square plus b square omega square. So if you see here, when omega is equal to omega 0, that is, this is the frequency in case of this oscillation frequency. This omega 0 was there here. So this omega 0 is the frequency of oscillation. This omega 0 is the frequency of oscillation, and this omega is the frequency of the applied force, frequency of the applied force. So when these two are equal, only then this amplitude will be maximum. So the maximum amplitude will be f0 divided by, this term will be 0, then it will be f0 by b omega. So this will be the maximum amplitude, and this condition is called as resonance condition. So this is the resonance condition where the amplitude is maximum. And also you can see that this b corresponds to this damping factor, like in previous we had here gamma. So this gamma is here b. So this b is the damping factor. So also due to this damping factor, because the damping is always there, even if we apply some force to maintain its amplitude constant, or even if we can increase if the condition of resonance satisfied. So however, there will be damping factor. So in case of heavy damping, the amplitude will not be so large. So this is the frequency f. So as you can see, in case of heavy damping, the amplitude will be minimum. If the damping is medium, then the amplitude will be more. And in case of resonance condition or small damping, the amplitude will be high. So if you see the graphs, or if we compare different graphs corresponding, if you compare different graphs corresponding to different types of oscillations, this is the natural oscillation. This natural oscillation is otherwise called as free oscillation, because we discussed that in case of free oscillation, this amplitude remains same, this amplitude is constant, and also the time period, that is the interval between two maximas or two minimas, is same. So the time period also same. So the time period is constant and the amplitude is constant. So this is the example of free oscillation. Now, when there is a but all the oscillations in nature are not free. Most of the oscillations are damped due to some external factors like friction or air friction. So as time increases, its amplitude goes on decreasing and it decreases exponentially. So this is the e to the power minus x. This is the e to the power minus x. Here x, this x is nothing. Suppose you can take it x0. Suppose, so this is the amplitude profile, and this is the oscillation, because oscillation is always there, but the change in amplitude will be in minus or exponentially decaying mode. And again, this is the resonance condition when the amplitude, when the frequency of oscillation omega 0 matches with the frequency of the force which is being applied, or the periodic force frequency, then the at the end of each oscillation, when it reaches some particular point, if the force is applied, then the amplitude of the system will go on increasing. So this is the resonance condition if the two frequencies are equal. So this is the example. If you see here, if the for a f0, again the amplitude, so suppose the oscillation, this is the oscillation, and it's same oscillation, we like the example we had discussed here. This is the example when you play with a toy that involves an object, it is being suspended on your finger. In the beginning, if you hold your finger still, the object bounces up and down, but with a small amount of damping. So when you move your finger up and down, so depending upon the resonance condition, that is depending upon the frequency of oscillation or frequency of oscillation and frequency of your movement of finger. If the movement of finger is low, again the dimension, again the amplitude will be less. If the frequency is quite high, again the amplitude will be less. But if the frequency of periodic force is equal to the frequency of oscillation, then the amplitude will be increasing. So this is the case of resonance, which is f equal to f0. Or so now these are the different types of oscillations. Now talking about different systems that that is used to demonstrate oscillation. So every one of you must be knowing about simple pendulum. So basically, simple pendulum is a mass. This is the mass m. It is being suspended by means of a string. Suppose the length of the string is L. So it is at its equilibrium position. So if you shift it, or if you take it to a height h, then at this point there will be the weight mg is always acting in downward direction, but there will be two components. So there will be mg sin theta and mg cos theta. So this is theta. This is mg sin theta. Actually, both these are actually perpendicular to each other. So due to this component mg sin theta, it will again come back to its original position, and due to its inertia, it overshoots the original position and it goes here. So in this way, it oscillates. So if you calculate, the frequency of oscillation will be, or the time period of oscillation will be t equals to 2 pi L by G root over. So this is the time period of oscillation, or frequency of oscillation is 1 by 2 pi G by L to the power half. So this is the time period of oscillation of a simple pendulum. Here this is a fixed point. From this point, the pendulum is suspended, and when we disturb it from its equilibrium position, it undergoes oscillation. There is another type of pendulum which is called as compound pendulum. In case of compound pendulum, but in case of simple pendulum, what was there? The length of the length L of the string through which it was suspended was taken to be negligible when compared to its. Basically, this mass is called as bob, bob. So mass of this bob, or suspending mass. But here it is a whole body, so it will be having moment of inertia, because since it is oscillating, means it there will be having some point, it will be having some center of mass. So in case of compound pendulum, suppose this is the point, pivot point or P, and we are oscillating it, and this is its center of mass, that is the mass of the whole mass of the object is concentrated here. Then we will be calculating fast the moment of inertia, because during oscillation it is doing circular motion like this. So if you calculate a time period, it will be t equals to 2 pi into I divided by mgd, or I here I is the moment of inertia, and d is the distance of this pivot point from the center of mass. So this is d, and this is the formula for time period of oscillation for a compound pendulum. Now coupled pendulum, in case of coupled pendulum, what happens? There are two pendulums which are coupled by means of a spring. So this is a spring mass system. There are two pendulums. So there will be, this is theta 1 and theta 2. If the since there is a spring, it will compress and it will extend. So the theta 1 and theta 2 will be different. But in case of simple pendulum, there is only one theta. Since we have coupled it, then corresponding to this spring, we'll be having two types of vibrations or two types of oscillations. So corresponding to each oscillation, there is a frequency of oscillation. So these are two types of oscillations. One is both the pendulum will be shifted in same direction. Like in this is theta 1 is in this direction, theta 2 is also in the same direction. So both are both the displacements is occurring in same direction, along same direction, and this is called as one normal mode of frequency. So this is basically equal, like the simple pendulum. So the frequency of oscillation will be similar to that of simple pendulum, that is angular frequency omega p is equal to g by l. But in case of another mode, like there is the spring is so one oscillation will be like this and another oscillation will be in this direction. They will be compressing and there will be, but one oscillation is like this. So these are two sets of oscillation. One set of oscillation is this, another set of oscillation is this. The frequency of oscillation, since it has two different types of oscillations, there are two different frequency of oscillation. So it will be g by l root, but here in this case it will be g by l plus 2 k by m root. So there are two normal frequency modes. Now, in the experiment, there was another type of pendulum which is called as pulse pendulum. Basically, here we can demonstrate. Demonstrate different types of oscillation, like forced oscillation and damped oscillation, free oscillation. Eventually, free oscillation is nothing but damped oscillation. With time, the amplitude is damped or amplitude reduces. So basically, this is a set of for poles pendulum. This is the ammeter or milliammeter. Then this is the circuit, and this is the motor which is used to apply the force. Now the Pohl's wheel or rotating torsional pendulum. This is the Pohl's wheel. Allows for the investigation of force harmonic rotary oscillation. So this is rotary oscillation. Like if you rotate in this way, then this is a spring mass system. This spring will contract and this spring will expand, and due to this energy stored in the spring, then it will again undergo oscillation in opposite direction. So this is the Pohl's pendulum setup. For this purpose, the oscillating system is connected to an excitation linkage is driven by adjustable speed DC motor, so that the restoring spring periodically extends and compresses. So we apply some force in terms of current. So when we increase current, then due to the generation of magnetic field, then there is the generation of eddy current, and due to that there is some energy stored in the system. So there is a motor in the setup. So in lecture you have learned or discussed about the setup and how to perform different types of experiments. So I will be giving you a few minutes, 5 or 10 minutes, to go through all these types of oscillations and all the concept we discussed. So then we will be solving a few problems. So please go through all these information that I now discussed with you. And after that, we will be solving a few problems which will be related to these types of oscillations and other things. So let's start solving questions related to oscillations. So now the question says, if the length of simple pendulum is increased by 44%, then what is the change in time period of the pendulum? So we have already discussed about simple pendulum and the time period of its oscillation. So using this formula, you can easily calculate. So I will be giving you a few minutes to try it, and then I will solve it. So please calculate and tell me what will be the change in time period if the length of the pendulum is decreased by 44%. Yes, anybody solved it? Question says, if the length of the pendulum is increased by 44%. So we know the time period of oscillation of a simple pendulum is T is equal to 2 pi into L by G root over. So since we are taking here the change in length and time period, so we can, the G is obviously constant. So if you take derivative, or if you take a log and then again take derivative, then it will be, suppose this will be ln t and it will be ln 2 pi L by G root over. So it will be ln t equal to ln 2 pi plus half ln L by G. Suppose this G is constant, so we can say that after taking, so if you differentiate it, then it will be dt by t. This is constant, so derivative will be 0. It will be half into dl by L. So dt by t is equals to half into dl by L. So from this relation, we can again say that dl by l equal to 2 into it actually, because we are given with the change in length and we need to calculate the change in time. So directly from here, you can easily say that this dl by l means is the ratio of change in length to the original length. So here it is given this length of the pendulum is increased by 44%. So this dl by l is 44%. So this dl by l is 44%. So if you calculate, then dt by t will be 44 into 1 by 2. They will be 22%. So this is the correct answer. The correct answer is 22% because the time period is direct proportional to square root of length. So when you take log on both sides and take derivative of, or take fast derivative, then the change in time to original time will be half of change in length to original length. So the change in time is half of 44, that is 22%. So this is the correct answer, 22%. Now, is there any doubt in this question? Anyone? Okay, so let's go towards next question. Now the question says, for a particle executing simple harmonic motion, the kinetic energy K is given by K equals to K0 sin square omega t. The maximum value of kinetic energy will be what? Yes, can anyone tell me what will be the maximum value of kinetic energy? Basically, this question is a bit simple, but we can make it so we can also try to calculate other things. So we can say that so maximum value, it's obvious because the maximum value, can anyone tell me what will be the maximum value of sine square omega t? Can anyone tell me what will be the maximum value of sine square omega t? Yes. So the maximum value of sine square omega t is 1. So if you simply, if from this, it will be k0 into 1. So k0, because we know the maximum value of sine square omega t and cos square omega t both are 1. But if you, if the question is when the value will be maximum, then what we can do? First, will be taking the derivative, like this is k is equals to k0 sine square omega t. So for maximum value, this dk square by dt square will be less than 0, is not it? So if you calculate dk by dt, it will be how much? K0 d by dt of sine square omega t. This is K0 2 sine omega t into cos omega t into omega. Then again d square k by dt square you can calculate. If you equate it, then you can obtain that at maximum value of energy 1 minus cos 2 omega t will be how much? Will be 2. Because cos 2 omega t has the value of minus 1, so it will be 1 minus of minus 1 equal to 2. So if you do it, or if you calculate it, it will be how much? It will be cos 2 omega t equal to minus 1. Then which value of cos is minus 1? This is cos pi. Cos 0 is 1, cos pi is minus 1. So this is cos pi. So 2 omega t equal to pi. Then omega will be pi by 2 into t. Sorry, pi by 2 to t. So, or again we can say that t is equal to pi by 2 omega. So this is the time period, and after this time period, if omega is the frequency of oscillation, after this time period pi by 2 omega, the energy of the simple harmonic oscillator will be maximum. Then the next question, the question says the period of a simple pendulum is doubled when its length is doubled, that mass of the bulb is doubled, the length is made 4 times, and the mass of the bulb and length of the pendulum are doubled. So basically it is a simple question. You can directly tell it from the expression for its time period. So please calculate and tell me what will be the correct answer in this question. Yes, can anyone tell me what will be the correct answer? Yes, can anyone tell me what will be the correct answer? So from the expression we know t is equals to 2 pi L by G root or t. So the period of time is doubled. So this t will be t prime will be 2t. All these are constant. So since t is directly proportional to root L, then 2t will be what? Directly proportional to so 2t will be directly proportional to 2 into root L, is not it? So it will be directly proportional to root of 4L. So when the length is increased 4 times, then the time period of pendulum will be doubled or 2 times. So if the length is made 4 times, so if the length is made 4 times, the time period of simple pendulum will be doubled. So this is the correct answer. And again, The next question is the frequency of simple harmonic motion is 0.05 hertz. Its time period is how much? Yes, can anyone tell me? It's a very easy question. Can anyone tell me what will be the frequency of a simple harmonic motion? If the frequency of simple harmonic motion is 0.05 hertz, then what will be its time period? Yes, can anyone tell me?
So 20 seconds.
Yes, because we all know time period is 1 by frequency. So it will be 1 by 0.05 or it will be 20 seconds. Again, now this is in hertz, but if I will say the angular frequency is 0.05 radian per second, then can anyone tell me what will be the time period? Can anyone calculate and tell me what will be the time period? If the angular frequency is 0.05 radian per second, because since your direct frequency is given, we can directly calculate 1 by f. Time period is 1 by frequency. But here it is given the angular frequency 0.05 radian per second. When it is in radian per second, so it is angular frequency. So can anyone tell me what will be the time period in this case?
So 40 pi.
Sorry,
40 pi.
yes, because omega in terms of time period we can write 2 pi by t. So 2 pi by t is 0.05. So E will be 2 by 0.05 pi. It will be 40 pi. Into 3.142 second. Time, since it is time, it will be always in second. 40 pi second. So the next, the question says a body of mass 36 gram moves with simple harmonic motion of amplitude 13 centimeter and a time period t equal to 12 second. At time t equals to 0, x is plus 13 centimeter. Find the displacement at time t equal to 2 second. Yes, so can anyone tell me what will be the answer in this question? It is given the mass of the body is 36 gram and the motion is simple harmonic motion. Amplitude is 13 centimeter. Time period is 12 second. Then at time t equal to 0, the value of x is 13 centimeter. Then at time t equal to 2, what will be the value? Yes, can anyone tell me?
So 6.5 centimeter.
So how did you calculate?
Sir, it is x equal to a cos omega t.
Yes, because we know in case of simple harmonic motion, the position at time t, x function of t is given by a cos omega t. So if you put t at t equal to 0, x at 0 will be a cos omega into 0, which is a into 1 or a. So here a is given 13 centimeters, so a is 13 centimeter, which is again given in the question that at time t equal to 0, x is plus 13 centimeter. So when time t equal to 2 seconds, then what will be the value? Then t2 will be a cos omega into 2. A is 13, so it will be 13 into cos omega is nothing but 2 pi by t into 2. It is 13 into cos 2 pi divided by t is also given, t is 12 seconds. So t is 12 seconds. Sorry, we don't need unit here. 12 into 2, it will be 13 into cos pi by 3. Cos pi by 3 is how much? Cos pi by 3 is cos 60. Cos 60 is 1 by 2. So this 13 into 1 by 2, 6.5 centimeters. So this is the correct answer. This is 6.5 centimeters. So at time t equal to 0, x is 13 centimeter. So the displacement is 6.5 centimeter at 2 seconds, because when a body is undergoing simple harmonic motion, the position at time t is given by x as a function of t is a cos omega t. So when you put value of t is equal to 2 seconds, and also we know the time period of oscillation is given in the question. This is 12 seconds, and the amplitude of oscillation is 13 centimeter. So if you put all the values and calculate, it is coming out to be 6.5 centimeter. Is this clear to all of you? Then the last question of today's session. For a simple pendulum, the graph between t square and L is whether it is a straight line passing through the origin, whether it is parabola, whether it is an ellipse, or whether it is a circle. So can anyone tell me what will be the graph between t square and L? Yes. Can anyone tell me what is the equation of straight line? Yes. Can anyone tell me what is the equation of straight line?
So y equal to mx plus c.
So y equals to mx plus c. So what is m? What is m and what is c?
So m is slope and c is where the line passes through.
M is slope and c is what?
Where the line passes through.
Passes through which axis?
Uh,
So when you in this equation, when you put x equal to 0, then y becomes c. So at x equal to 0, y is c. This is which intercept? At x0, it passes through a y-axis, so this is y-intercept, is not it? So m is slope and x is and c is y-intercept. That is at x equal to 0, y is equal to c. So the curve crosses y-axis at c. Again, what is the equation of circle?
So x square plus y square equal to r square, where r is the radius of the circle.
So x square plus y square equal to r square is the equation of circle. Basically, this is the equation of circle of radius r and its center at 0, 0. Because in generalized form, this is x minus x1 square plus y minus y1 square equals to r square. Because here x square plus y square means x minus x1, y minus y1. Here x1 is 0 and y1 is 0. So all are 0. So this is the equation of circle with center at origin. X square plus y square equal to r square. Then x square minus y square equal to r square is, sorry, x square minus y square equal to r square is the so what is the expression for parabola? What is the equation of parabola? This is y square equal to 4ax. And equation of ellipse is x square. The equation of ellipse is basically circle is a special case of ellipse. So here in both the cases r square is r is equal. In case of ellipse, since there are semi-major axis and semi-minor axis, it will be x square by a square plus y square by b square equal to 1. This is the equations of different conic sections. So now the question says, for a simple pendulum, what will be the graph between t square and L? We know t is 2 pi L by g root over. So t square will be 4 pi square L by g, is not it? So t square equal to 4 pi square by g into L. Let me add another side. So what we get? T square is 4 pi square by g into L. So if you compare it with y equal to mx plus c. So what is m here? Can anyone tell me what is m here? M is 4 pi square by g. If you take t square along y-axis and L along x-axis, then slope is 4 pi square by g. This is slope. And this c is 0. C0 means at x equal to 0, y is 0. So the line passes through origin. So this is the straight line. T square is along y-axis, L is along x-axis, and the line passes through origin. This is origin 0, 0, and this slope, this is theta. So tan theta is 4 pi square by g. Equation of the graph between t square and L is a straight line which passes through origin. Is it clear to all of you? we discuss a few things, do we solve a few problems related to the coefficient of viscosity of a liquid and different types of, and mainly we discuss problems based on oscillations. So in next class, I will try to solve a few problems related to forced oscillations, damped oscillations, and we will be solving a few problems related to compound pendulum. There is another spring pendulum or compound pendulum, or we can say there is coupled pendulum also. So I'll be trying to solve a few problems related to that because these problems are quite simple. So we'll be solving a bit hard problems. So that's it for today. In next class, we'll be discussing a few problems and we'll be also discussing about the waves, that is transverse wave, longitudinal waves, and we'll be solving a problem. So thank you all for joining in today's session. That's it.